All right, let's have a look at another E2 elimination reaction and try to work through it. Let's cover the basics. What are the basics of an E2 elimination reaction? A strong base, which is charged and wants a hydrogen, will rip off a hydrogen from an unsuspecting molecule. And we need to know exactly where it's going to start by ripping off that hydrogen, and then a cascade will follow. The cascade will take the remaining sigma bond electrons and allow the carbon, which had that hydrogen, to use them somewhere else to form a pi bond, and then you'll end up with a double bond, and the bromine will leave. So let's get started. So given this molecule right here, where should the attack occur? Well, so first of all, the attack should happen somewhere related to the carbon with the bromine, right? So it should happen on something related to this bromine, so it should happen on this carbon. Now, this carbon does not have a hydrogen, so the attack can take place on to the left or right of it. So can't happen on that carbon, so it could happen to the left or right of it. So we are looking at something with bromine leaving, which would be probably the last step. We're gonna end up with something like CH, either on this side, or we're gonna, that's if this one loses its hydrogen. But if this one loses its hydrogen, we're gonna end up with something like this, and the rest of whatever has to be drawn, whatever the rest of the molecule looks like, right? So now we have decided the places where a cascade will originate. Either this will lose a hydrogen, and then we'll take the remaining electrons once that hydrogen is gone, supply them to the double bond with carbon, so that bromine gets kicked off, because carbon can't have more than 4 bonds, right? So, or we'll appropriate hydrogen from here. The strong bond will rip off a hydrogen, and then the remaining electrons that still belong to carbon will be used to form a pi double bond, and then this bromine will say, hey, you can't have 5 bonds, carbon, I'm leaving, right? So one of those two things will happen. Hopefully with that, I'll draw this. We figured out pretty much how to decide the places where the cascade will begin. So let's draw one of them. So assuming it is right here, CH3, and this is a strong base. So, and there's a CH3 here. Now I would like to attack right here because that is directly related to bromine, but there's another place that could work, which is right over here. We could attack this, and we could rip off that hydrogen. Let's draw this better than that. Let's say the hydrogens are on the top and the bottom. That's far prettier. And there we go. We attack and we take that hydrogen away. We got 2 electrons as part of this sigma bond, and we're saying, okay, we'll use them over here, because going to the right would make no sense, kind of. I mean, it's far more reasonable to kick off a bromine, because bromine is a good leaving group. And if you don't know about leaving groups, probably I should make another video about that. But bromine is such an excellent leaving group that rather than flipping to the right, it's going to flip to the left and say, yeah, that's where I want to be. I want to get bromine to go away. So it's going to start turning, and it's going to end up right there. And well, carbon can have only 4 bonds, and we have to get rid of one. And bromine is a good leaving group, so it packs up its bags, takes some electrons with it, and goes away. And this is all in one step. You can call them parallel step, or you can call them steps in concert, or you can just call that concerted reaction. So that's one, and that should leave us with something like double C, and one of the H's goes away, so just CH and CH3, and of course the base got what it wanted, which was an extra hydrogen. It ripped that off. So CH3C double bonded to CH3, and of course there was this metal hanging around on top. That's still there. So that's one option. Oh, of course there's a bromine now floating around because it's happy with its packed bags. So the other way we said it could happen is it could attack, let's draw that better, CH3, which was on the left side. It could attack there. So CH3O minus would say, I'm going to take this away. And this is, well, I'm going to flip over to somewhere where there's a good leaving group, and I'm going to form a connection with this. And bromine's just going to go bye-bye, and everything else stays where it is, right? Bromine got eliminated. Actually, hydrogen and bromine got eliminated. That's why I call it a cascade or avalanche of sorts. This CH2 still has, what it originally had. No problem there. The CH3 had what it originally had. And yeah, that yields again a CH3OH because the base got its way. The bromine still left. And now you're looking at CH2 double bonded to carbon, and everything else is as it was, other than the fact that the bromine left. Yeah. So now which one is the majority group? Majority group. How do we decide the majority product? Actually, not group, majority product. And for that, we can just take a look at the substituents. So, more substituents of an alkene carbon. So what's an alkene carbon? These together are alkene carbons. These together are alkene carbons. Knowing that, now we're ready. We can say, hey, there's one group here. There's two groups here. There's three groups here. So this is, the number here is 3. And over here, the number is 1. And this is an ethyl. So 1 ethyl, 1 methyl. Here's 3 methyls. The size apparently doesn't matter. And all that matters is how many there are. So here we have 2. Here we have 3. So this is the major product. Let's check. Yes. So again, I'll do this again. 1, 2, and 3, right? Because it's not one carbon that forms, how to say this? It's talking about how many substituents are there on alkene carbons as plural. So these are alkene carbons. And together, these one had 3, and the next one has just 2 substituents. So the one with the more substituents, wins right here. And that's what we found out as a majority product. So hopefully with that, both you and I feel plenty comfortable with E2 elimination reactions.